In this rational function, we're trying to find zeros, local minimax, and inflection points. So the first thing we'll do is look for zeros. So we look for zeros in the numerator, where the numerator is equal to 0, and we're going to find that x is equal to 0. So that's going to be our first point. In fact, I'm going to put that into our table of values here, and we can plot that point at 0, 0. So the next thing I'll do is look for the denominator, and in the denominator we're looking to see if we have any zeros for vertical asymptotes. So e to the x is never equal to 0. So in this case here, because of that, we don't have any vertical asymptotes, so no vertical asymptotes. So then we're going to look at horizontal asymptotes. So we're going to look at endpoint behavior as x tends to infinity and negative infinity. So as x tends to infinity, we end up with x over e to the x. Well, this is a weak function over a strong function. The strong function is going to dominate, and we're going to end up tending towards 0. So we're going to end up with a horizontal asymptote going to the right towards 0. Looking at what's happening as we go to the left, we have something slightly different because we end up with negative infinity on top, but e to the negative infinity is 0. So we're tending towards 0, and it's always positive, so we're going to end up with negative divided by positive, or negative infinity. So what's going to happen on the left here then? It's going to dive down. Okay, so we've established no vertical asymptotes, zeros, horizontal asymptotes, and endpoint behavior. So we want to look for local min and maxes. So we need a derivative. So differentiating this, we differentiate the numerator, multiply it by the denominator, minus the numerator times the derivative of the denominator, all over the denominator squared. We can simplify this by factoring out the e, and then we can cancel that extra e factor in the numerator and denominator. So we end up with 1 minus x in the numerator over e to the 1x in the denominator. And we want to know where this derivative is equal to 0. And it's equal to 0 at x equals 1. So I'm going to put that in my table of values. That's a potential min or max. Plugging that into my equation, when x is 1, f of 1 is equal to 1 over e. And just here, we've established that that's about 0.4. So that's going to be 1 over e, which is approximately 0.4. So at x equals 1, right around here, we're going to have y equals about 0.4. Okay, sorry, 0.4 is going to be more like this. Okay, so putting that in my slope chart then, at x equals 1, at x equals 1, we have 0 slope, and we want to test the slopes on both sides of that. So we're going to test f prime at 0. Plugging in 0 into that equation, we get positive over e to the x is always positive, so that is positive slope. So we know it's going up. It looks like a potential max, so we're going to test the slope on the other side of that. So at x equals 2, we're going to end up with negative in the numerator, positive in the denominator. So that's going to be negative slope. So we have positive slope here, negative slope here. So our slope chart indicates that that point is going to be a maximum. So we know it's going to kind of go up like that. So we've established the first derivative and the slope chart for the first derivative. Now we want to find the concavity. So the concavity, we're going to find the second derivative. So we're going to differentiate that expression again. So differentiating 1 minus x, we get negative 1 times the denominator minus 1 minus x times the derivative of the denominator. And then we're going to square that denominator using our quotient rule. and then we can simplify this. We end up with negative e to the x minus 1 e to the x, and then plus, looking at the signs, we're going to plus x e to the x. And that's all over e to the 2x. We can see that there's a common factor of e to the x that cancels out. Combining my like terms, I get negative 2 e to the x plus x e to the x. Factoring out my e to the x, I'm going to end up with x minus 2, and then we can cancel that extra factor out. So we have x minus 2 over e to the 1x. So we want to know where the second derivative is equal to 0. There's no undefined values because, again, the denominator is never equal to 0. So we want to, finding out when that is equal to 0, we get x equals 2. So there's a potential inflection point at x equals 2 because there's 0 concavity there. So testing my second derivative, so the second derivative, we're going to test it at x equals 1. So plugging in 1 into that, actually 0 is an easier number. So we're going to plug 0 in there. We end up with negative in the numerator, and e to the x is always positive. So we have negative concavity on this side. So at x equals 0, we have negative concavity. And we can see that that's the case when we have this function here. We can see from the slope chart that that matches. And then we're going to test the concavity at x equals 3. So the numerator is positive, and again, the denominator remains positive. So we end up with positive concavity on this side. The change in concavity indicates an inflection point. So that is an inflection point at x equals 2. So I'm going to put that into my table of values, x equals 2. Find the y coordinate. We get 2 over e squared, which we worked out here as approximately 0.3. So we're going to put that into the graph. There's a point there, and that indicates an inflection point. A little bit higher, I think. This coordinate here indicates an inflection point. So we have all the parts of the graph now. We know that it goes down to infinity. It's going to come, it's going to come up through there, max point, change concavity, and follow the asymptote. So we're going to draw that in full. So from negative infinity, comes up through the 0, through the max point. At this point, it changes concavity, and then it curves towards the horizontal asymptote. Okay, so that's what our graph is going to look like. And again, we can check this on Desmos, and we should be checking these on Desmos after to see how our analysis matches the actual graph.